In this video, we are going to walk through another example with power series, finding the interval of convergence. So let's take a look at our example. We're going to be looking at the series that sums from 1 to infinity the addends square root of n, x to the n, over 3 to the n. This is a power series because the n's involved in the equation come from the sum, but the variable x is viewed as something we have control over. And what we're trying to do is determine the values of x for which we could plug a value in, and this infinite series would converge. In order to determine the interval of convergence, the first thing we do is find the radius of convergence, almost always through the ratio test. So when performing the ratio test, I do things one step at a time in order to break down what needs to be done and work in small pieces to try to prevent mistakes. The first step is to determine the absolute value of the n plus first addend. Now the square root is always giving positive values, so I don't need to put any absolute value signs around the square root of n plus 1. X, however, a priori can be any real number, and it's very plausible that the value of x is negative. Therefore, we do need to put absolute value signs around our x. Because we're only plugging in positive values for n, the quantity 3 to the n plus 1 is also positive, and we don't need any absolute value signs there. What we do on the right-hand side of the equal sign is simply break up the way that we're writing absolute value of x to the n plus 1 and 3 to the n plus 1 for future cancellations. The second step when performing the ratio test is quite similar to step 1, but here we determine the absolute value of a sub n. There's almost less to do here. We simply look at the addends and put absolute value signs where they're needed. And as we discussed in step 1, the only term that requires an absolute value sign here is the quantity involving x. The third step is to simplify the ratio of the n plus first addend to the nth addend. When we begin with this, we simply take the output from step 1 and divide it by the output from step 2. But seeing as this is a quotient of quotients, that's real difficult to think about. We take the reciprocal of the denominator and perform a multiplication instead. This is where our work in step 1 to rewrite those quantities to the n plus first power becomes helpful, as we have highlighted terms in the numerator and denominator that match and can therefore be canceled. Combining all of that work, we find that the simplified version of the ratio of the n plus first term to the nth term is the quantity square root of n plus 1 multiplied by the absolute value of x, all divided by 3 square root of n. Notice that we cannot cancel the square root of n in the denominator with the square root of n plus 1 in the numerator algebraically, but some type of quote-unquote canceling will occur later in the process. As a fourth step, we are now going to compute the ratio rho via a limit as n approaches infinity. Substituting in the output from step 3, because we are now taking a limit, we are allowed to ignore the plus 1 term, as it is not contributing to the limit as n is approaching infinity of this value. Once we neglect that plus 1 term, given that it is not contributing to this limiting process, we find that we have a square root of n in the numerator and a square root of n in the denominator, and those values do in fact cancel, meaning that our value of rho is equal to the quantity absolute value of x divided by 3. Our fifth step is in fact the final step of the ratio test. As we've now gotten an expression for rho from the previous step, we would like to know when that rho value is less than 1 in order to determine the x values for which this series converges according to the ratio test. If we set up our inequality, rho is less than 1, substituting in the absolute value of x over 3 for rho, we can remove the absolute value sign by sandwiching the internal value x over 3 between negative 1 and 1, or more generally, if there were an a here, we would remove the absolute value signs by substituting this in between negative a, and we clear the denominator, multiplying all parts of the inequality by 3 to obtain our final inequality. Negative 3 is less than x is less than 3. This tells us that our radius of convergence, that is the distance between the center of the series and one of the endpoints, is equal to 3, because 0 is the center of our series, and the distance between either 0 and 3 or 0 and -3 is equal to 3. At this point, we have determined the radius of convergence, but what we do not know for sure is the exact behavior of the series when x is equal to -3 and when x is equal to 3, because our ratio test is inconclusive when rho is equal to 1. This makes the last step of our computation of the interval of convergence to manually enter the endpoints of the interval one by one and use a different series test to determine convergence or divergence. Beginning with the left endpoint, plugging in -3 for x, we can distribute the n to both the -1 and the 3 and rewrite the series in this way. We can then focus on the two terms that are going to cancel from numerator and denominator, and we are left with the series as n goes from 1 to infinity, -1 to the nth power multiplied by the square root of n when we plug in our left endpoint. Notice that when we take the limit of those addends as n approaches infinity, that limit does not exist. It oscillates back and forth between a very high positive value and a very low negative value. Thus, this series cannot converge by the nth term test for divergence. The computation at the right endpoint is similar. Here, we plug in 3 for x, and our cancellation is more plain, and we're left without an alternator, simply summing addends of the form square root of n. Here, when we take the limit as n approaches infinity of our addends, the limit exists and is infinity. However, this is not a value of 0. And what this means is that this series diverges, again by the nth term test for divergence. All of this to say that the interval of convergence here is -3 is less than x is less than 3. And we are positive that we don't need to add any equal signs on these less than symbols because we have physically checked that our series diverges at both endpoints. And that's it, a full worked out example of checking a series for the interval of convergence.